Hi guys, so this is just going to be a quick video on alternating current. We haven't really had a chance to talk about this, and so far everything that we've been working on has been direct current, and so I wanted to give you a little more information on this, fill in a couple details. So uh, everything that we've been doing so far has been DC, which just means it's constant in time, so we can think of that as just a horizontal line if we were to graph the current as a function of time. Now, where we're headed is alternating current, and that would be sine wave, cosine wave, and we could, of course, uh, describe this mathematically as a sine or a cosine, and your book uses sine. So the parts that you have in here, this is the the amplitude, and this is the angular frequency. And what this means is if you think about the argument for the sine function has to be an angle. And so what this is omega equals 2 pi times the frequency in hertz. So when you multiply that by an amount of time, you end up with an angle in here, and you can take a sine of it. And you can think of this as the connection between angle and how many times the cycle is happening. So if you imagine, going all the way around the circle, that would be 2 pi in angle. And so you would accumulate 2 pi per amount of time. So 2 pi times frequency. And I would mention, the frequency that's coming out of the wall is 60 hertz. So this is probably the most common AC frequency that we deal with. And, we can connect this to voltage. Just with Ohm's law, we know that V equals IR. So you can imagine that, if you multiply this by the resistance, you would get the voltage, and it would behave the same mathematically. There would be, some amplitude, the max voltage, and it would just be proportional to the current. So the same math. And when we think about, voltage coming out of an outlet, you know how we talk about this as being 120 volts? Well, what does that mean exactly? This is a specific definition. It's called an RMS voltage. So let's walk through what that means, because I think that'll help clarify what we are talking about when we're talking about AC voltage and current. So an RMS is a square root of the average of the square of the voltage. So, and it's useful, I think, to think of what this looks like graphically. So if you were to look at the average voltage, what that would amount to would be you would integrate the voltage over one period. And what that would equal would be, notice we have this this function. So I should say this would be from 0 to t. So you'd find the value of that over one period and divide by the period. So if you do that with sine or cosine, you can see that since that thing is positive just as much as it's negative, this would equal 0. Now, when we look at the average of the voltage squared, we do the same approach. You'd integrate over one period v squared and divide by one period. And what that would look like, so you'd have v naught squared sine squared omega t dt. Now, this is not so obvious how to integrate, so let's look at that. Oh, and we should say, graphically what that would look like is you would see immediately it's not going to be 0. You square that function, you get something like that. So this would be, v naught, and this would be v naught squared. Okay, so what is the value of this integral? Well, let's sort this out a little bit. So we can pull out the constants. And really what we're integrating then is sine squared. And of course, there's lots of different ways that you could do this. Probably an integral you've dealt with in calc, I'd suspect. Probably the easiest way to mess with this is to use trig identity. That sine squared of x is equal to 1/2 1 minus cosine 2x. So we can apply that to this problem. So we would have 1/2 times 1 minus cosine of 2 omega t. And now we have basically our integral has two pieces. So this first thing, we just have 1. So this would end up being, let's pull the 1/2 out. So we would have, the integral of 1 from 0 to t. So we'd pick up a factor of t. And then for this piece, the integral of cosine would give us sine, let's see here, 2 omega t. We would have a factor of 2 omega. And this would be evaluated from 0 to t. Now, notice, recall, what is omega? It's 2 pi times f. So really what you have in here is 2 times 2 pi f times the period. So f and t are, reciprocals. So this would be 1. So you have an integral number of 2 pi. And so the upper limit of this would be 0, and the lower limit would also be 0. So this whole thing would be 0. And so what you're left with is just v naught squared over t times 1/2 t. And in other words, the average of v squared is v naught squared over 2. And as a result, the root mean squared, the RMS voltage would be v naught over root 2. Okay. So both of these pieces of information are pretty useful. And it's useful, I think, to see where that comes from. So you compute the average. You do this integral, you divide it by the amount of time that you're averaging over, and you would find this connection between the max voltage and the average voltage. And where this can be useful is, well, it's useful for a number of things, but let's connect back to our examples. So I told you that, you know, the voltage that's coming out of the wall is 120 volts. Well, that's the VRMS. And so this equals the max voltage over root 2. So the max voltage coming out of the wall is root 2 times 120, which is more like 170 volts. Which is kind of interesting because we don't usually think of, you know, the wall voltage as being higher, but it is, or the maximum value is anyway. Okay. So what else did I want to mention about this? So of course this would be the same situation for current. Same math. In other words, IRMS is going to equal the maximum current over root 2. Actually, let me also add this up here, that this is VRMS, just to be super explicit. So the current, you know, behaves the same way. Let me just draw a cartoon too to show you this. So there's different ways that people specify AC voltages. VRMS is probably the most common way. Oof, that's not very good. So the thing that I want to just point out is that, you know, V naught would be the maximum value. VRMS is less. And then there's another fairly common one, which is peak to peak. So the other way of specifying this would be to say the voltage peak to peak, which would, you know, you can see that would be 2 times V naught. So like a lot of things, this is a good example of where it's important to just be explicit about what you're actually talking about. These different systems, it's simple enough to connect, to convert between them. But if you just say, you know, V, it's not necessarily clear what you're talking about. So it's good to just offer more detail. So something that we can immediately apply this to is power. And when we talked about power before, you know, we connected that power was the current times the voltage. And we had a couple other definitions as well. You know, we could, with Ohm's law, we could express this as I squared R, or we could equivalently have this as V squared over R. And let's just put this in with our definition for what the voltage looks like. So remember, this would be V naught times sine omega t. And then if we just square this thing over R, this would be the definition for the voltage, or for the power rather. Now, most of the time we would talk about the average power. And the convenient thing is that the average power, we would perform this same procedure, right? Where you would integrate over some period and figure out what the average is, but we've actually already done that. The average power would look like the average of v squared, just divided by r. And we already know what the average of v squared is. We have it up here. V naught squared over 2. So we would pick up just an r in the denominator. And we could equivalently say that this is the same thing as, VRMS squared over r. And the really nice thing about this is just that when we're talking about AC or DC, this simple power expression is the same, which is pretty convenient. But it's good to be aware of the fact, to see that these are the same thing. And this, I would mention too, this holds for what we did with current as well. So I squared RMS times R would also be the power. So these are also useful. So let's look at an example with this. So one example would just be from lab. Let's look at an example from lab. So remember, we've been looking at 10 volts for the experiment this week. It said to set the voltmeter to 10 volts AC. So what does that mean exactly? Well, that's a RMS voltage. So what would the peak voltage correspond to? We know that VRMS is less than the peak voltage by a factor of root 2. So in other words, V naught in this case would be root 2 times 10 volts. And so this is more like 14 volts. That's just a simple example of the, the terminology. Another example, let's think about a toaster. So let me give a little more room here. What would be the RMS current and peak current for a 1200 watt toaster? So this question gives us another opportunity to just practice with this terminology and these simple definitions. So we know the average power is equal to VRMS squared over the resistance. And I should say, since this is plugged into, presumably this is plugged into a wall, toaster, this would also be 120 volts RMS. So we could solve this. So there's different ways we could go about solving this. One way would be to say, okay, let's solve for the resistance, and then if we know the resistance, we could solve for the current. So let's do that first. So this would equal VRMS squared over the power. So this would be 120 volts squared over our 1200 watts. And this would give us, show us that the resistance for the toaster was 12 ohms. And then we could use, our other definition of power, that's IRMS times the resistance. And this would let us solve for IRMS as just being the square root of the average power over the resistance. Um, so this would give us 10 amps. And then the other, we could also get this directly by just noting that our other definition for power still holds, that it's just IV, so except it would be I RMS times V RMS. And you can see that we can get this directly. In other words, I RMS would also equal our 1200 divided by 120, and that would give us 10. So, different ways, 6 of one, half a dozen of the other. And then we can see, we could relate this to the peak current by noting that I RMS is, of course, I naught over root 2. So the peak current would be, 10 times a factor of root 2. So that would give us about 14 amps. So hopefully, these examples showing you these definitions helps you when you go to solve problems with this stuff. I think that you find that it's pretty similar to solving problems with DC voltages and currents, but I think it's good for you to see where those definitions are coming from, because these things sound very similar. And I guess, let me just add up here. I'll just add that this is also equal to IRMS times VRMS. So we have a lot of different definitions for power, and they're the same thing as the same math as what we had with DC.